Hi, welcome to our second module in our CXC Chemistry 2020 examination review. Today we will try to explain the changes between the three states of matter in terms of energy and arrangement of particles. We will consider freezing, melting, boiling, evaporation, sublimation, condensation, heating, and cooling curves. Here we have a nice schematic showing us how we interchange from one state of matter to the next. As you can see, when we are in the gaseous state, the particles are far apart. This is because the particles have high kinetic energy, as they also have low intermolecular forces between them, and there is no orderly arrangement of the particles. If we choose to change from a gas to a liquid, then we have to change two things. We have to change the order and arrangement of the particles so that they can come closer together, like those found in the liquids, which are found in clusters. And in order for us to do this, we need to decrease the kinetic energy of our particles so that they will move less. And we also need to form forces of attraction between the particles so that they can change the liquid state. This is known as condensation. Now, because of the differences in the kinetic energy and the forces of attraction in the various states, those two factors have to be addressed whenever we are changing state. So as we see, if we are changing from a gas to a liquid, we have to decrease the kinetic energy because the gases have high kinetic energy. The liquids have a moderate kinetic energy, so therefore the energy has to be decreased. Secondly, gases have weak forces of attraction, whereas liquids have moderate forces of attraction. That means that you are trying to make stronger forces of attraction for your liquid. Now, the process by which this is done is known as condensation. And this process is an exothermic process. It means that for you to convert a gas to a liquid, heat energy has to be released, meaning that some of the kinetic energy has to be lost from the gas for it to become the liquid. The opposite of the process is true. If we are in the liquid state and we aim to change to the gaseous state, then it means that we have to do a process which is endothermic. We have to absorb energy from the environment in order for us to raise the kinetic energy of our liquid particles and in order for us to destroy some of the forces of attraction. There is a method for us to change directly from a gaseous state to a solid state, which is known as sublimation, which we will discuss later. But in essence, you can see that solids have strong forces of attraction, they have low kinetic energy, and the gases are the opposite. So there is a process whereby we can move directly from the solid state to the gaseous state or from the gaseous state and back. And there are only two main substances that will do this, including ammonium chloride and iodine. Now let's consider how we change from the liquid state to the solid state. If we want to move from the liquid to the solid, as we can see, we'd have to decrease the kinetic energy of our liquid, so we'd have to cool it down. And that would be done under the process of freezing. We also need to form more forces of attraction because solids have more forces of attraction than liquid. And that would be achieved by removing heat. So freezing is essentially an exothermic process as heat is being removed. The opposite is true. From the solid to the liquid, we would have melting in which we're adding energy, and that would be an exothermic process. Let us now consider what happens during the evaporation of a liquid in which some of the particles of the liquid are able to escape into the gaseous state. In the liquid, all the particles do not have the same amount of kinetic energy. There are some particles that naturally do have a high level of kinetic energy. Some have medium kinetic energy, and there are some that have low kinetic energy. If the particles that have high kinetic energy are found at the surface of the liquid, they are able to overcome the attractive forces that are in the liquid and are able to escape to become a gas. So in evaporation, in essence, what we have is that we have high energy kinetic particles or particles with high kinetic energy at the surface of the liquid being able to leave to become the gaseous state. However, the other liquid particles that have medium kinetic energy or low energy have to remain in the body of the liquid. This can occur at any temperature. Here we have a beaker showing evaporation. That it shows that there are no bubbles in the liquid when we have evaporation taking place, because really we only have high energy kinetic energy particles that are leaving from the surface of the liquid. On the other hand, boiling is a process that occurs at a fixed temperature depending on what is the overall atmospheric pressure. Now for boiling, it requires that we add kinetic energy. So we need to heat the liquid. By heating the liquid, we are adding kinetic energy. And what we're essentially doing is that we're increasing the kinetic energy of all the particles in the liquid. There are some particles that already had high kinetic energy. They will be the first to leave in the gaseous state. But those that were in the liquid that had moderate and low kinetic energy, well, when we add the heat, we are also giving them high kinetic energy levels so that they can also escape and go into the gaseous phase. So what you will notice in the liquid is that you will have bubbles. This is because some of the particles in the liquid have gained enough kinetic energy to be converted into the gaseous state. Boiling occurs at a fixed temperature. Evaporation occurs at all temperatures. There is no fixed temperature where this process occurs. It's only taking place at the surface of the liquid. Boiling takes place at a fixed temperature and pressure. It involves the entire liquid in which all the particles have gained sufficient kinetic energy so that they can escape into the gaseous state. Let us consider a cooling curve here. This shows us what are the changes in temperatures with time that occurs when you're changing from one state of matter to the next. Whenever you notice that the temperature has started at a high level and it gradually cools down, then it is a cooling curve. We will see on another slide the opposite of what is a heating curve, and at that point you're starting down here where the temperature is low and you're gradually increasing the temperature. The key thing I want you to get from this is that whenever you want to change state, whether you're changing from a gas to a liquid, there are two stages that must occur. So change of state requires two stages. In stage A of the process, what you do first is that you have to decrease the kinetic energy of your particles. So if you're at the gaseous state in which your particles have high kinetic energy and you're hoping to become a liquid, then you must go through stage A where you drop the kinetic energy of your particles. As you drop the kinetic energy, you will notice that the graph slopes downwards because the temperature is decreasing. So there is a direct relationship between kinetic energy and temperature. As the kinetic energy decreases, so will the temperature. However, we'll get to the second stage, stage B, and we still haven't completed our change of state. As we said, we have to go through the two stages in order for the process to be complete. In our second stage, what we are now doing is that we are no longer decreasing the kinetic energy of our particles, but instead we are focused on forming new forces of attraction. Now, in this stage, notice that the graph remains flat. So as time progresses, the temperature remains constant. That's because the kinetic energy is not changing. However, we are only using our time to form new forces of attraction. Now, while we are in this first stage, we have our particles completely in the gaseous state. However, when we get to this flat line where we're actually forming new forces of attraction, you are going to find some particles in the gaseous state, some particles in the liquid state. However, when we get to the end of this line at this point, this is where the complete change of state has occurred. In this case, because we're cooling down from a gas to a liquid, it is known as the condensation point. Or if we were coming up the other way, it would have been considered a boiling point as well. So at this point, we only now have a liquid. We have completely changed from a gas to a liquid. Now, if we consider or change from a liquid to a solid, we will see that we will also go through the same two stages that we just went through. First, in stage A, we will have a decrease in the temperature, and this is because we are decreasing the kinetic energy of the particles. And the temperature will also decrease. And then we get to the point where the graph becomes flat again. This is stage B of the process. In this portion, we are forming new forces of attraction. And so the temperature has remained constant. Remember now, once we're coming down this slope, we only have one state. So here we only have particles in a liquid state. However, once we get along this flat portion, we now have a mixture of the two states. Some of the particles are in the liquid state, some are in the solid state, but it's only when we get to the very end of this line that we can say that there has been a full change of state and that we will only have solid particles as of this point going forward. So as you can see, if we continue to go down, we would only have solid particles. As mentioned before, we also have a heating curve, which is the exact opposite of what we saw before, which was a cooling curve. It's just that we have started in the opposite direction. So in this case, we have started with a solid and we want to change it into a liquid. We have to go through the 2 stages as we discussed before. So at first we will heat up the solid, we will raise the kinetic energy of the particles, and you will notice that the temperature is increasing. Then we get to this flat portion. That's because at this point we are breaking up forces of attraction. Now remember, along the flat portion we will have both states existing. So we would have solid and liquid here, but right here at the very end of this flat portion is where we'll actually have the melting point, at the very end of the flat portion. And that is when we have completely converted all our solid into a liquid. And if we continue to raise the temperature, then we'll see that the temperature of the liquid will increase. And then we'll get to another flat portion. And at this point, we will now be converting our liquid into a gas. And we will be forming new forces of attraction, breaking forces of attraction, so that we can convert our liquid into a gas. We would have both states of matter here. We would have liquid and gas present along this flat portion, but at the time when we get to this end of the line, we will only have the gaseous state existing from that point forward. Let's now consider sublimation. In this process, we directly change from a solid to a gas. We do not go through a liquid intermediate. A substance sublimes because the forces between the particles in a liquid state are too weak to remain in this state. Essentially, if we first was to melt our solid to convert it into a liquid, the particles will not stay in the liquid state for a very long time because the forces of attraction are too weak. So immediately the liquid would change into a solid. So essentially it's as if you did not see the liquid state. It essentially just moves from solid to gas. Now, sublimation occurs because the particles at the surface have enough energy to break away from the solid to become a gas. So remember, we said that in any substance at all the particles do not have the same amount of kinetic energy. There are some particles that have high kinetic energy. There are some that have medium, and there are some that have low kinetic energy. It so happens that in some solids, the particles that have high kinetic energy, the kinetic energy is so high that they can actually escape and just become a gaseous state, change into the gaseous state directly. As we will see with solid iodine, it directly moves from a solid into a gas because the energy, some of the particles at the surface have very high kinetic energy, which allows them to do so. And in a similar breath, we can do the opposite, where we can have vapor that if we cool it, it goes directly into the solid state. This is another schematic diagram looking at sublimation, showing that this process also occurs with dry ice, carbon dioxide. Here we can have the solid ice. And normally it would melt to become the liquid, and then the liquid would evaporate to become the gas. However, sublimation bypasses this process. It directly moves from the solid to the gaseous state. And that is because, as we said, some of the particles in solid have such high kinetic energies that they can immediately escape to the gaseous state without having to pass through the liquid state. The particles of note that do sublimation for the CXC purposes is ammonium chloride and iodine. So I have indicated the examples here. The ammonium chloride and the iodine are classic substances that you should know that they sublime. Here we have an experiment illustrating the sublimation of ammonium chloride. We have solid ammonium chloride here that is being heated. Now, instead of it becoming liquid ammonium chloride, it eventually becomes a vapor. And then when it gets to this cooler part of the funnel, it solidifies again. So essentially what has happened is that it sublimed here when we heated it. It became a vapor, but as soon as the vapor found a cool area, it eventually solidified again. And this is an experiment that illustrates sublimation. This is the end of Module 2. In Module 3, we will continue to discuss the mixtures and how we separate mixtures. Thank you for watching.